Hi, I'm Antonio Sala, and in this second video we'll continue with the manipulability analysis of a planar robotic manipulator. In a first video, we spoke about the model, the Jacobian, and its singular value decomposition, and then in the second video we'll define the manipulability ellipsoid, and we'll graphically represent the principal maneuvers and also compare with the polyhedron geometry when maximum velocities are in the unit cube instead of the unit sphere as the ellipsoid geometry explicitly assumes. So if we review the modeling, we have positions of all joints and the end-effector depending on the sinus and cosinus of three joint angles. So we write this in MATLAB, and we also compile these symbolic expressions onto a numeric function for plots and animations, returning a 4x2 matrix of the xy positions of the elements of the robot given the three angles. The end-effector position was named R, and we are studying manipulability in this pose with these angles, and we can see here the pose of the planar robot. End-effector velocity can be computed by the Jacobian matrix of the end-effector position, a matrix of partial derivatives of xy coordinates with respect to theta 1, 2, 3 input angles. So the Jacobian is a 2 times 3 matrix, which has these numbers. We did some scaling in order to incorporate the knowledge that the third articulation could move faster than the other two. And then we can carry out the singular value decomposition of the scaled Jacobian to get the principal maneuvers, one in which I have a kinematic gain gear ratio, let's say, of 7, and another one with a kinematic gain of 2. In fact, the Jacobian can be computed not only with the partial derivatives of the end-effector positions, but the partial derivatives of all joints position. So if I take derivatives of these xy positions of 3 elements, 6 in total, with respect to 3 angles, I get a total Jacobian, let's say, of dimensions 6 times 3, but the end-effector Jacobian is the one corresponding to the last 2 rows. Note that I scaled as well, so these are scaled units in the input side, and we did the singular value decomposition of the 2 rows. So if I change coordinates so that inputs are the principal input maneuvers, this is equivalent to multiplying these all Jacobian scaled by the V matrix of the input directions of SVD, then we get the principal end-effector maneuvers in the last 2 rows. The modulus of these 2 numbers here, first column, is 7, and the modulus of this one is 2, equal to the principal gains, and then the rest of the rows are x and y velocities in intermediate lengths associated to those end-effector principal maneuvers. Well, they are, a bunch of numbers that we'll see better when we do some graphics. For the moment being, we'll leave them here and we'll come back later on. So let us now start with the main goal of this video, which is defining the so-called manipulability ellipsoid. First, we'll forget about the scaling, because in most textbooks they do like this. Scaling is a trivial change of variable, so we'll do them later on without any complications. For the moment being, let us imagine that I have this velocity equation of a given manipulator with the Jacobian at a particular pose, and that I know that the Euclidean norm of the joint velocities, the norm of the dot q vector, is less than 1. So this will mean that the joint velocities will be in the unit sphere. Then, which will be the set of attainable end-effector velocities with this dot q unit sphere constraint? Well, this is the main result. This equation describes an ellipsoid called the manipulability ellipsoid, and we are going to prove that indeed that is the case. So we'll need to resort to pseudo-inverses because, well, in our particular setup we have 2 end-effector velocities and 3 joint velocities. Then, if I wish to have some prefixed end-effector velocity, I have an infinite number of solutions to this system of 2 equations with 3 unknowns. Then the minimum norm solution, the least square solution, is given by this pseudo-inverse of the Jacobian times the desired velocity. Okay, desired velocity, come on, well, we want, let's say, maximum velocity. So we'll check which values of velocity can be plugged into this formula to give this optimal joint angular speed vector having norm less than 1. So, of course, the least square solutions is the one to explore, because if the result of this operation has not norm less than 1, then no other solution will lie into the unit sphere. So this is the main idea in this proof. If pseudo-inverse of j times v has norm less than 1, then the end-effector velocity is feasible, and if it has norm greater than 1, then it's infeasible. So, if we recall our linear algebra background, this is the formula of the pseudo-inverse we need to use. So, I put here the least square solution, that one. I put here the transpose, and carrying out operations, we see that j transposed with this inverse cancel out. So at the end, we are able to prove our main result, that if the end-effector velocity vector v fulfills this equation, then it is feasible with an input angular speed vector of norm less than 1. And this equation, as j transpose, is a positive definite matrix. It's the equation of an ellipsoid, which is called manipulability ellipsoid, and which will be plotted in a minute. The line to plot it is just changing the Jacobian to the Jacobian scaled. Then we have this matrix, which is the one there in the middle. So v transposed, this m1 inverted v must be less than 1. So this line draws such an ellipsoid centered in the end-effector. Rop is the R position of the end-effector at the operation point, the pose selected. I mean, this is just cosmetic, okay? The velocity ellipsoid is centered at 0, but putting that ellipsoid at the end-effector somehow gets a pretty picture, because we are speaking about end-effector velocities. We'll later on discuss the rest of plotting commands, but this dashed red line is the manipulability ellipsoid. And as I said, it has unit of speed. The arrows also have unit of speed. So even if I superimposed a position plot of the robot, we are not speaking about positions, but about speeds. So now let's delve into what these arrows are. And these arrows are the principal maneuvers. Let us recall relationship with the SVD decomposition, because if in this expression I say that J has this singular value decomposition, then J transposed has this thing, and again V transposed V cancel out and give identity because V is an orthogonal matrix, so we get this US S transposed U transposed, and S transposed is just the diagonal matrix. So this U transposed is the diagonalization of the positive definite matrix defining the manipulability ellipsoid. So the semi-axis of the ellipsoid, or ellipse in this 2D case, are the columns of U, which were the output directions of the SVD of the Jacobian, and the square root of the eigenvalues are the length of the semi-axis, and that square root of t is just the elements of the diagonal of S, so the singular values. So with this, we can say that, looking again at this SVD, the major axis of the ellipsoid will have a modulus of 6.96, and we'll have this direction, something pointing to the right and a bit downwards, and the shorter semi-axis of the ellipsoid will have 2 meters second modulus, and we'll have this direction, which will be perpendicular to the red one, pointing basically up. So these principal maneuvers 1 and 2 are the yellow and purple arrows of length 7 and 2 depicted here. And what are the other yellow and purple arrows? Well, they are the principal maneuver 1. This is the yellow arrow in the end-effector, and these are the arrows I drew the first and second intermediate joints, and likewise these 6 numbers grouped 2 by 2 xy are the arrows corresponding to the second principal maneuver, and indeed this is the null maneuver, no movement of the end-effector, but in the null maneuver I do have movement of the intermediate joints. We'll simulate that in next video. And then I did draw 2 arrows in those intermediate joints in another color, in green, representing the null maneuver. So with some angular speed corresponding to the third column of the V matrix in the SVD decomposition, these 2 joints move a little bit in these directions, but end-effector does not move. So the maximum gain maneuver, maximum speed of the end-effector with unit norm input is the yellow arrow. The purple arrow is the second principal maneuver with a minimum gain, of course, excepting the null space maneuvers. And then in green we have a null space maneuver that does not move at all the end-effector. So this is the interpretation of the manipulability ellipsoid and the principal maneuvers. Also, the arrows are plotted with the command quiver, so you can download the code and examine the documentation to understand how to do this in MATLAB. But the important thing I am interested on is on understanding the meaning of those principal maneuvers. We'll finish the video with a last observation saying that, okay, the underlying assumption of this ellipsoid stuff is that the scaled velocity was in the unit sphere. But come on, when I speak about saturation of physical motors, it's more likely that the extreme velocities lie not in the unit sphere but in the unit cube or hypercube in which vertices are combinations of +1 and -1. So, which is the conservatism of the ellipse approach versus this polyhedral approach? Well, with this line, dot qn vert are the normalized vertices of the unit hypercube, all the 8 combinations of 1 minus 1, 1 1 1, 1 1 minus 1, 1 minus 1 1, etc. And of course, multiplying by the scaling EQ, I get the vertices of maximum allowed joint angular speeds in physical units, not normalized. So, if I multiply the Jacobian by those vortex velocities, I get the true extreme velocities. Then, with this convexual stuff that, okay, you can read the documentation, internalize why it works. I don't wish to delve into details here for brevity. Then, okay, with this code, we can plot the actual polygon unit cube multiplied by the Jacobian. So we can see that the ellipse approach is conservative. We can get larger speeds, but on the other hand, the ellipse allows me to connect with least squares problems, and maybe those least square solutions are the ones that I might be using in real-time kinematic control of this, with the Jacobian and its pseudo-inverse. And also the ellipse approach allows me to connect with the SVD and the principal maneuvers. But the polygon approach is just the image of a bunch of points. Also in higher dimensions, the number of vertices will increase. To summarize and end the video, in this video we discussed the definition and interpretation of the manipulability ellipsoid and its relationship with the principal maneuvers, SVD of the Jacobian, and also we discussed the advantages and disadvantages with respect to a polyhedron cube-based approach, which would be, the exact way of determining the vertex velocities achievable by my manipulator and the angular speed Hall limits. Each approach has advantages and drawbacks, so we'll finish the discussion. We end the video here. Thanks for watching.